This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 6 of Week 5. Gas turbines and the Brayton cycle. 4 processes: compress, burn, expand, exhaust. We turn one pressure ratio into a thermal efficiency, then meet the trap that separates gas turbines from steam plants, a compressor that eats most of the turbine's work. Brayton is 4 processes. 1. The compressor squeezes air isentropically. Temperature and pressure climb together. 2. The combustor adds heat at constant pressure, reaching the turbine inlet temperature, the hottest point in the cycle. 3. The turbine expands the hot gas isentropically and drives the shaft. 4. Exhaust rejects heat at constant pressure and resets the air. A real gas turbine is open. It breathes fresh air and dumps exhaust. The closed air standard model just swaps that exhaust for a heat rejection step, so the same air recirculates. Same 4 boxes as Rankine, but the working fluid stays a gas all the way around. No phase change, no steam tables. Because compression and expansion are isentropic, one pressure ratio sets both temperature jumps. The compressor pressure ratio, RP, equals P2 over P1, and the turbine drops that same ratio in reverse. The temperature ratio across each is RP raised to K-1 over K, where K is the specific heat ratio. That exponent is the only place K enters. Compute the group RP raised to the K-1 over K once, call it theta, and then T2 is theta times T1, T4 is T3 over theta, 2 multiplications instead of 2 exponentials. Know the pressure ratio, K, and the 2 endpoint temperatures, and every state falls out. The variable table for every Brayton problem. Pressure ratio RP and specific heat ratio K, both pure numbers. The specific heat CP for air about 1.005 kilojoules per kilogram Kelvin. Compressor inlet temperature T1, usually ambient. Turbine inlet temperature T3, the firing temperature. And the 3 answers: thermal efficiency, back work ratio, and net specific work. The only constants you bring are CP and K for the gas. Cold air standard means you hold both at room temperature air values the whole way around. Exactly what the exam expects, unless it says otherwise. Here is the payoff. For the ideal Brayton cycle, thermal efficiency is 1 minus 1 over RP to the K-1 over K. It depends only on the pressure ratio and the specific heat ratio, not on how hot you fire the turbine. Raise the pressure ratio and efficiency rises, but with diminishing returns. This is the headline trap. The formula is built on the pressure ratio P2 over P1, not a temperature ratio. The firing temperature controls the net work and the back work ratio, but it cancels right out of the efficiency. Net work is turbine work minus compressor work, each a CP times a temperature drop. The back work ratio is compressor work over turbine work. How much of the gross output the compressor immediately claws back. In a steam plant, the pump's backwork ratio is 1 or 2%. Pumping a liquid is nearly free. In a gas turbine, the compressor squeezes a low-density gas, so the backwork ratio runs 40 to 80%. That is the structural difference. A gas turbine throws away most of its turbine work just to drive its own compressor. It is also why these machines fire so hot. A higher turbine inlet temperature shrinks the backwork ratio and lifts net work. Worked problem. An ideal air standard gas turbine, pressure ratio 10. Air enters the compressor at 300 Kelvin. The combustor adds heat at constant pressure up to the firing temperature, 1300 Kelvin, at the turbine inlet. The turbine expands the gas and delivers the net shaft work, exhausting at state 4. On the temperature entropy diagram, the cycle is 2 vertical isentropes, compressor up, turbine down, joined by 2 constant pressure curves that diverge to the right. No dome, because air is an ideal gas. Find the thermal efficiency, the backwork ratio, and the net specific work. The plan: compute the isentropic group RP to the K-1 over K. Get the 2 unknown temperatures. Take efficiencies straight from 1 minus 1 over that group. Then, the backwork ratio and net work from the 4 temperatures. Compute the isentropic group once. Rp to the k minus 1 over k is about 1.931. Multiply T1 by it for the compressor exit, 579 Kelvin. Divide T3 by it for the turbine exit, 673 Kelvin. Thermal efficiency is just 1 minus 1 over that group, about 48.2%. Notice it never touched the inlet temperatures, pressure ratio, and the specific heat ratio alone. Now the work. Turbine work is Cp times the turbine temperature drop, about 630 kilojoules per kilogram. Compressor work is Cp times the compressor temperature rise, about 281. The back work ratio is their quotient, 0.45. The compressor consumes 45% of the gross turbine output. Net work is the difference, about 349 kilojoules per kilogram. Cross-check. Net work over heat-in gives 0.482, matching the efficiency. Forget the compressor work, and you overstate net work by 80%. The most expensive Brayton mistake there is. 4 traps. 1. Forgetting the compressor work. The back work ratio runs 40 to 80%, not the 1% of a steam pump. Net work is turbine minus compressor. 2. Putting a temperature ratio in the efficiency formula. It uses the pressure ratio, P2 over P1. Firing temperature never appears. 3. Flipping the exponent. It is K minus 1 over K, about 0.29 for air, less than 1. Invert it and the answer explodes. 4. Using the wrong temperature scale. Isentropic relations demand absolute temperature, Kelvin or Rankine. Celsius or Fahrenheit makes the ratio meaningless. Bookmark the Brayton pages. The 4 processes: isentropic compression, constant pressure heat in; isentropic expansion, constant pressure heat out; the isentropic relation that turns the pressure ratio into a temperature ratio; the pressure ratio definition; the thermal efficiency, pressure ratio, and the specific heat ratio only; the net work and back work ratio; and the ideal gas specific heats. Note the regeneration variant adds a heat exchanger that recovers exhaust heat and lifts efficiency at low pressure ratios. A common follow-up twist. You now own the gas turbine, efficiency set by the pressure ratio, and the back work ratio that explains where the turbine work goes. Notice the exhaust left at 673 Kelvin, far hotter than ambient. That wasted heat is the whole reason combined cycles exist. Next topic, we bolt a Rankine bottoming cycle onto that hot exhaust and push plant efficiency past 60%. Bring today's exhaust temperature, it becomes the heat source for the steam side.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.